Hello guys, so today in today's video I'll be going over the Diels-Alder reaction and some practice questions. Okay, so first of all we need to know the general properties or general characteristics of a Diels-Alder reaction. In a Diels-Alder reaction, you're going to have a 1,3 conjugated 1,3 conjugated diene. Okay, and this 1,3 conjugated diene has to be in a S-cis conformation. So something like this. All right, so you will see the reason why this is 1,3 conjugated. You see, if you count 1, 2, 3, right? The dienes are in 1,3 proximity to each other. The pi bonds, right? So that is the one where the 1,3 comes from, and then the cis part comes from the fact that both sides are facing the same direction, right? So if we were to draw a dashed line, we'll see that both alkene are facing in the same way. So that's what I mean by S-cis conformation. All right. Oops. All right. So now the other part of a Diels-Alder reaction is to have a dienophile. So dienophile is, diene is the part of the diene comes from the fact that you have a diene, and then the phile is loving, right? So a dienophile is something that loves a diene. So that would be an alkene, meaning your double bond, or an alkyne, your triple bond. Okay, so you need to have these two present for a Diels-Alder reaction. Okay, also your product is going to be a 6-membered ring. Your product is going to include a 6-membered ring, I should say. So we'll go more in depth with this as we go on. So let's look at the first. So for the first two structures, if you're doing the homework, this is going to be part 2. For the first two structures, the dienes, we're going to determine if these dienes can participate in a Diels-Alder reaction. So let's look at this one. So looking at this, the way that the two pi bonds are placed, we can determine that this will not be able to participate in a Diels-Alder reaction because it is not conjugated. Right? If we count from the first pi bond, that's 1, 2, 3, 4. So this is a 1,4 diene, not a 1,3 diene. So that will not be able to participate. Let's look at the second one. So if we look at the second one, it is a diene, right? And 1, 2, the proximity is 1,3, right? We do have a 1,3, so let's check that. 1,3 conjugated diene. However, is this in a S-cis conformation? Let's look. It's not. If I were to draw a fence like this, they're not really facing the same direction. And the other question we should ask ourselves is, can we rotate a sigma bond? So let's say we have something like this, right? We could rotate this sigma bond because you can rotate sigma bonds to where so that the two sides of the diene can face the same direction. But in this case, we have a ring, so that is not possible. So we cannot use this diene as well for a Diels-Alder reaction. So if you look at this third question, this third question is not determining whether we will be able to use the diene. This is asking for us to provide a mechanism and also a product. So yes, we do have a 1,3 conjugated S-cis diene, and we also have a dienophile, our alkene. Okay, so let's go ahead and see what the reaction mechanism look like. So the reaction will start from the dienophile, right? It's gonna make a new bond with that carbon, right? And being that that is too carbon, we have too much. This carbon will have too much bond. We'll have to break this bond and put it between carbon 2 and 3. Okay, and then since that will will give too much bond to these two carbons, would have to also break that bond to form a new bond with that structure. So let's draw what this will look like as a product. Remember I said that you're gonna end up with a product with a 6-membered ring. So you can go ahead and first draw the 6-membered ring and then, fill out the rest. But let's go step by step. If you look at our diene, it has 4 carbons, right? So let's first draw that 4 carbon, right, without the pi bonds. So since we broke the first bond, we don't need to draw that. We made a new bond right here between carbons 2 and 3, right? And we formed a new bond right here, right? If you go back to the arrows, you'll be able to see this. Okay, so let's make the parts of this dienophile green. Let's make it green. So you see that there is one side of the this side of the dienophile, right? It won't have that pi bond any longer because it's this pi bond any longer, because that is what we broke the first time. Okay, but it will still have everything else. Okay, so this would be our product, right? It has a 6-membered ring, and then the remaining part of the dienophile attached to it. Okay, so let's go on to the next question. So if you look at this next question, you'll notice that we have an alkyne instead. So what will we do for this alkyne? It's basically the same mechanism. You attack from the dienophile, you attack the diene. You attack the diene, and then you make a bond between carbons 2 and 3, and you form a bond from the last pi bond. You form a bond again to the alkyne. So let's see what that looks like again. So this, I forgot to mention that this reaction takes place when you have heat, right? So again, let's draw our 4 carbon coming from our diene, right? And then let's draw that new bond we made between carbons 2 and 3. Okay, and let's draw these other 2 new bonds that we made right here. So let us also keep in mind that the triple bond, okay, will still have that side of it, and then we'll also have 1 pi bond, because we only broke 1 pi bond from that triple bond. Okay, and then it has 2 cyanides that are coming off of it. So this will be your final structure. Okay, in order to make sure that you're doing this right, you may also want to count how many carbons you started with and how many carbons you're ending with. So from we already know from here we have 4 carbons, 1, 2, 3, 4, and then from here we have 1, 2, 3, 4, right? So we should end up with 8 carbons in total. So we see our ring is 1, 2, 3, 4, 5, 6, right? And then 7, 8. So we do end up with the right amount of carbon. So that is correct. Okay, and as you can see, the product does have a 6-membered ring in it. So this is our final product. So let's look at another situation. This time our diene is cyclic, right? Previously we've looked at our diene that is acyclic. Now our diene is cyclic. How do we go about this? So whenever you have a cyclic, whenever you have a cyclic diene, you're going to end up with a bicyclic product. Or actually you end up with a bicyclic product if your dienophile is also cyclic, but a cyclic diene will give you a bridge. Okay, so let's see how this goes. So again, the dienophile will attack, but this time the question is, where would the dienophile attack? It will still attack from that carbon, the first carbon with the double bond, and then we're going to make a bond between this carbon and this carbon. Okay, and then we'll form another bond back to the dienophile. Okay, this is happening in the presence of heat. Okay, so what you want to understand is that in this scenario, notice we didn't touch this part of the diene. That part will be pushed up. Okay, let's see what that looks like. So again, let's do what we've been doing. We draw that 4 carbon coming from the diene. We draw the new bond. Let me redraw this. Oops. Okay, we draw the new bond between carbons 2 and 3. Okay, we draw the new bond to the dienophile. Okay, and then we do have to keep in mind that the dienophile has a side, right? And then it has two cyanides coming off of it in the cis position, right? So you can either draw this as 2 wedges or 2 dashes. Okay, but what happens, the question is, what happens to this part of the diene? That part of the diene actually gets pushed up like that, right? So this is kind of like a 2D way of drawing it. Okay, oops. Yeah, so you just have to draw that bridge. So whenever you have something that's in front of or coming off of that diene as a cyclic, as being cyclic, it's gonna be pushed up. Okay, so that is it for today's video on the reaction for on the mechanism for Diels-Alder's reaction. If you have any questions, let me know. I hope you have a wonderful day. Thank you.